my name is Rob Hackman. I'm a lecturer at the University of Waterloo in the David R. Cheriton School of Computer Science. And today I'm going to be giving a talk about how computers actually work. So you've probably used a computer before, and you probably have a vague sense of what a computer is. It's a whole bunch of circuitry where electrical signals flow through the circuitry and tell it to do specific tasks. Now the question is, how? And so in order to understand this, let's first talk about a more simple machine. For example, a stopwatch. And a stopwatch has three main functions. Start time, set a lap. So start time will start the timer and it will start counting up from 0. Set lap will reset the counter to 0 while keeping a cumulative total of the time so far, so you can have multiple times stored within one bigger time. And then stop, which will stop the timing. So when we think of a stopwatch, the way that this would work is there'd be three, maybe two buttons if start time and stop are on the same button. And this would be a simple set of circuitry such that when you click the start time button, a signal flows through the circuitry, which enables the circuitry that starts the timing to begin, and then it will probably do some kind of a loop throughout that circuitry to keep ticking each time a second passes or millisecond, so on and so forth. Set lap, similarly, will be another button that will then send a electrical signal through the circuit, which will then tell it to store the current time and then update the timer shown to 0 and start counting from there so that we can store a bunch of different laps out of a total time ran. And then stop, of course, will stop the timing and perhaps display the total time. And so stop may send an electrical signal. It may actually also be tied to the start time button and may stop sending the signal that start time had sent. Now the question is, if we want a stopwatch to do something else, for example, play the game Pong, how would we get it to do that? And the answer is, we can't without actually opening up that stopwatch and rewiring the circuitry so that it can play the game Pong. Because a stopwatch, the circuitry does exactly these three tasks. However, with a computer, when we want to run a new program, we don't have to open it up and rewire the circuitry. So the question is, what makes the circuitry in a computer different than the circuitry in a stopwatch? And the answer is nothing. The circuitry is exactly the same. It's still just a bunch of wires that allow electrical signals to flow through or not flow through. And then the question is, how do we configure those so that they can be reprogrammable and do different tasks? And so it's not that the circuits themselves are reprogrammable, because that would just be rewiring a circuit. Instead, what it is we've decided to set up a set of instructions that circuit can receive through certain signals of high and low voltages that will tell it what to do. So to understand this, we first want to talk about the main architecture that pretty much all modern day computers are based on today. Now, they're not exactly this, but they're based on it and they follow it pretty close. And that is von Neumann architecture, named for John von Neumann, the man who came up with the idea. So the idea behind von Neumann architecture is quite simple. So we start with what we call a CPU, which you may already be familiar with the term. A CPU stands for a central processing unit. This is where the majority of the processing, the computing that a computer does, is done. But a CPU itself is actually broken up typically, at least under von Neumann architecture, into two distinct components. First, the ALU, or arithmetic logic unit, and second, the CU, or control unit. So the arithmetic logic unit does a couple of things for us. It handles math, such as addition, subtraction, and multiplication and division. It also handles our logical operators, such as ANDing two values together, ORing two values together, or negating a value. Now, you may not know what those mean, but we'll talk about it shortly. Second is our control unit. And what does our control unit do? Well, our control unit actually handles the flow of the programs that this computer is ultimately going to read. So, for example, this is going to receive a bunch of high and low voltage signals, and it's going to need to interpret them into a program. Well, some of those commands are going to be ultimately sent to the ALU to do math or logic, and some of them are commands for the control unit, which tells it things like skip over the next command you're about to receive, or skip over the next 10 commands you're about to receive, or go back 6 commands, all right? And it's a little bit more complex than that, but that's what we'll leave it at for there. Now, this is our circuitry that actually runs the program. Now, the question is, where do the programs come from? And so in von Neumann architecture, we have a third component here called the memory unit, MU, and the memory unit is where our programs are stored, all right? And our programs get read into the CPU, where they are then executed, but at the same time, the CPU can write out to the MU to store data. So under von Neumann architecture, our data that we're working with and our programs are actually stored in the exact same place. Now that's one of the ways that modern computers often differ from von Neumann architecture, is that the memory unit doesn't store, or you don't have one single store for both your program and your data, but that doesn't really change how a computer works. So altogether, this is our machine, okay? And then connected to our machine, we can have inputs or outputs from keyboards, whatever, or outputs to screens or whatever else you might have. But this is, in essence, a computer, all right? Now, we've got our ALU and we've got our CU, but what do they actually do? Well, we just discussed that a stopwatch, in order to change what it does, we would need to go in and rewire it. So why not devise a piece of circuitry that can do a bunch of set tasks, and instead, based on the signals that you send through it, it decides what tasks to do. And that brings us to what we call the instruction set of a machine. So what is the instruction set? Well, it's actually the set of codes that the designer of the CPU decided should be interpretable as certain commands. So remember that I said the ALU does things like addition, subtraction, multiplication, division, ands, ors, or nots. So instruction set needs to be a set of codes, set of predefined codes, that the circuitry is wired to interpret. Now, we're not going to get too in-depth about how this circuitry actually works, as that would take quite a bit of time. But what we're going to say is we're going to assume that we can create a circuit that checks if a voltage coming through a wire is high or low. And we're going to also assume that we can check if a series of these voltages are high or low. Okay? And so that's how we're going to define our instruction set. Our instruction set is going to be a set of codes that we decide ahead of time are going to mean certain things. So for example, if our arithmetic logic unit needs to be able to add two numbers together, we could say, okay, well the code for adding two numbers together is going to be 1, all right? And now I'm going to write 1 here, but we're going to talk about what this code actually looks like when it comes to a electrical signal. And then let's go ahead and say that subtract can be 2, all right? And then we're going to say let multiplication be 3, and let division be 4, okay? And then we're going to say let and be 5, or be 6, and not be 7, okay? And we're going to have a lot more codes than this, but we're just getting behind the idea of how do we design this circuitry. And so now that we know that we've said, okay, addition is 1, subtraction is 2, multiplication is 3, division is 4, and division is 4, and is 5, or is 6, and not 7, then that means that we can construct the arithmetic logic unit so that it receives a signal that looks like 1, 2, 3, 4, 5, 6, or 7. It then does this operation. Now, what is that signal going to look like? Well, a signal is going to look like a series of high or low voltages arrayed together to represent one value. And so what we're going to use to represent high or low voltages are going to be 0 for low voltage and 1 for high voltage. So in order to be able to show all of these numbers, we're going to need a few digits. Except in this case, we're not going to call them digits like we do when we work with our normal number system, base 10, that you're used to in math. We're going to call them bits, because this number system only has 2 values for each digit, 0 or 1, and that's the binary number system. And so digit is the decimal number system's unit, and we're going to use the binary system, so we say bit, B-I-T. All right. And so this is going to represent 1. 4 zeros followed by a 1. Now to represent 2, we have to say, okay, how do we represent 2? Remember that this is in our decimal number system. We don't have the number 2. All we have is 0 or 1. So if we added 1 to this already existing 1, what would happen? Well, it would become a 2. But we don't have 2. So in our normal number system, if that happened, we'd carry over to the next place to the left. And that's the same thing that we do here. So this becomes a 0, and we carry that over the next place to the left, but it becomes a 1. So the reason that this makes sense is in the decimal number system that you're used to, this represents the ones column, this represents the tens column, this represents the hundreds column, this represents the thousands column, so on and so forth. Well, what are all of those columns? Well, they're 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, so on and so forth. So these are just the powers of 10 because that's the base 10 number system. In the binary number system, each of these spaces to the left represents the next power of 2. So this first one is still our ones bit because anything to power 2 is 1. So this represents if we have a 1 or not. This next one, well, if this number represents 2, then that's probably our 2, and it is. So that's 2 to the 1, just as this was 2 to the 0. Now this one would be 2 to the 3, which means that it is, or sorry, not 2 to the 3, 2 to the 2, which means that it's 4, all right? So the number 4 would be represented as 0, 0, 1, 0, 0. So now, that's our 2. So now how do we represent 3? Well, 3 is 2 plus 1. So we can actually just add these two numbers together, and that's our 3, because we have a 1 in the ones column, and we have a 1 in the twos column, or the 2 to the 0 and the 2 to the 1 column. So that's 1 plus 2 is 3, all right? Now, I'm not going to go much more into explaining what we're doing here, but just understand that these are the codes that mean these numbers. So our 4 is going to look like that, because that's the 4s column. Our 5 is going to be a 4 plus a 1, so it's going to look like that. And our 6 is going to be a 4 plus a 2, so it's going to look like that. And our 7 is going to be a 6 plus a 1, so it's going to look like that, okay? Now remember that these aren't actually going to be zeros and ones. The zeros are representing a low voltage signal, and the ones are representing a high voltage signal. But because there's only two potential values, low or high, we use zeros and ones to represent them. Now, these are our codes, or some of our codes. We'll have to have more. We don't have anything for the control unit to do yet. But if these are our codes, what are they applying to? So we say add has code 1, but what do we want to add, okay? And so that brings us to the next part of this. Our instruction set actually has a couple of parts, all right? It's got the operation code, or op code, which is the instruction to execute. So the op code can be 1 if it's add, it can be 2 if it's subtract, It can be 3 if it's mult, and it can be 4 if it's division, and if it's and, it can be 5, and if it's or, it can be 6, and if it's not, it can be 7. And of course, as I mentioned before, we have more codes than this, but let's start with this. So that's our op code. Now the question is, what do we apply these operators to? And so each code is actually more than just the operation code. Each code is also made up of at least 2 more components. And those components are, we can call them T1, T2, and T3 for target 1, target 2, and target 3. But I'd rather say source 1, source 2, and destination. Now, they may or may not be laid out like this. It may go opcode destination, source 1, source 2, depends on the system, but this is what we're going to work with. So source 1 and source 2 are the numbers to add together, or subtract, or multiply, or divide, or and, etc. And destination is the place to store them. So when I say source 1 and source 2 are the numbers, and destination is the place to store them, that should be a little bit strange, because now, how are these representing numbers and this is representing a place? Well, these are also representing a place. So in our computer, we're going to have these things called registers. And registers are a place where high or low voltages in a certain sequence that designates a number, just like these could designate the numbers 1 through 7, are stored. And instead, when we add, subtract, or apply our operators to two or 1 operands, what we end up with is actually numbers that designate the register numbers. All right? So this is a register number. This is a register number. And this is a register number. So what we're actually saying is take the values in these 2 registers and add them together if the opcode is 1 and store the result in the destination register. So if I said something like this, oh, can't write a 2, that was silly of me. If I say something like this, this says add together the number in register 1 with the number in register 1 and store the result in register 2. So if the number in register 1 was 5, we would add 5 and store the result in register 2, so we'd store 10 in register 2. So how does addition happen? Well, it's quite simple. It's just another circuit where these high and low voltages can flow through and get added together by combining the voltages. All right, not combining it as in, 5 volts and 5 volts becomes 10 volts. It's more the signals. So if we have, just like we did the addition of 1 and 1, it can combine those 2 circuits, see if those 2 circuits are both high voltage, and then output that the next bit, 2, the carry bit, should be set. And in general, that's how addition is done. All right. Now, we can do this with any of our operations. Now, this whole set of numbers would represent 1 instruction for the machine. So 0001, first 5 bits means the opcode. 0001, next 5 bits means source register 1. 0001, this means source register 2, the next 5 bits. And 00010 means the destination register. So the circuitry is set up to split up this. In this case, I've made it 20 bits long, which is not what a computer would really use, but we have this 20-bit long signal, so a signal of 20 high or low voltages. It reads the first 5, determines what it wants to do, reads the next 5 to determine where to grab a value from, next 5 for where to grab the next value from, and then the last 5 for where to place the result, and then the circuit does the operation and sends the result to where it needs to go. So that's all well and good, but how do our computers end up doing the more complicated things that we want them to do? For example, we write programs in higher level languages like JavaScript, Python that you might be familiar with, or C or C++, etc. and it gets turned into these instructions for our computer to understand. So how does that all end up happening? Well, we start by going one step up from machine code, because we can certainly write a program in this machine code. All right? So if I wanted to write a program that can write this value into machine code, then I could say, imagine that we have, 8 registers, R1, or we're going to start with R0 actually. Register 1, I'm actually only going to do 3 registers for the time being, because we just want to write a simple program. Now, how do we actually get numbers in here? Well, that's a little bit more complicated, but we're going to go ahead and assume that we have another instruction. All right? And this other instruction is going to be load integer. All right? So what is load integer? Well, its opcode is going to be 8, which is 0, 0, 1, 0, 0, or sorry, 0, 1, 0, 0, 0. That's our 8, okay? And load integer, instead of taking 2 source registers, is going to take a single integer and then the destination register. So when we write a load integer instruction, we write 0, 1, 0, 0. So these 5 bits are the opcode. But instead of those next 5 bits and the next 5 bits after that being the source and destination registers, instead, the next 10 bits are going to be the number to load. So these are actually going to be interpreted as an immediate value, all right? So this number, we could say is 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. So what number does that represent? Well, this is 1, this is 2, this would be 4, 8, 16, 32, 64. Well, everything before 64 was a 0, so this is 64 plus 2 plus 1 is 67. So this operation so far is saying load the number 67 somewhere. And then the last place, the destination register, is still the same. So if we write in the destination register 5 zeros to mean register 0, then this would load the number 67 into register 0. Of course, it wouldn't be in decimal, it would be a series of high and low voltages again, but that's what it would look like. So now we could write a very, very simple program with our set of instructions. We could load 2 numbers in and add them together and then divide them if we want. Or we could compute the sum of all numbers from 1 to n. So let's say that we want to calculate the sum of all numbers from 1 to 20. So the first thing that we want to do is we want to load the number 20 into one of our registers. So we write the 8 opcode, and then we write the number 20. So the number 20, I'm just going to write out all my bits first and then set them as I need them. So the number 20 is going to be 16 plus 4. So this is 1, 2, 4. So 4 should be on. And this is 8 and this is 16. So 16 should be on. So there we go. We have 20. All right. So this is our opcode. This is our immediate value to load. And now where are we going to load it? Well, let's load it into register 0. 1, 2, 3, 4, 5 zeros means register 0. All right. So this is load integer or load immediate number 20 into register 0. Okay? Now, we're probably all familiar, if you want the sum of the numbers from 1 to n, you add 1 to the number and then multiply the 2 numbers together and then divide by 2. So n times n plus 1 over 2. Okay? So then how can we do that? Well, we need to be able to add 1 to 20, okay? And so what we can do is we could load the number 1 into register 1. All right? And so this command is load immediate or load integer number 1 into register 1. All right? So then we load 1 into register 1. Now we want to add these two numbers together. So we use the opcode add, or 1, and we give it the two registers we want to add. So register 0 and register 1. And where do we want to store this number? Well, we can actually store it anywhere, except for we don't want to store it in register 0, because register 0 has 20, and we want to be able to multiply 20 by 21. So let's instead store this number back in register 1. All right, we could have stored it in register 2, but we're overwriting register 1 because why not? So this is add register 0 to register 1 and store the result in register 1. So 20 plus 1 becomes 21, and we store that in register 1. Now we can continue writing the program by simply saying, okay, multiply these two numbers, store the result in register 2. All right? Then we can store 2 somewhere in register 1 or register 0, and then we can say divide register 2 by the register that stores the number 2. And then that will be our result. So wherever that division gets stored is our result. So that's a simple program for calculating the sum of all numbers from 1 to 20. All right? And if we had some way of reading in an input, we could change 20 to be any number, because we've generalized it by adding 1 to the number that we loaded. All right? Now, this is quite a bit. If we had to write out our programs by writing all these zeros and ones, that would be a pain. Well, it turns out, one step up from these zeros and ones, which are called machine code, so our instruction set, the pure instructions are called machine code. One step up from that is a thing called assembly code. And assembly code is a basically shorthand for machine code that humans can write that has a direct translation to the machine code that the computer understands, the high and low voltages that we need to send through the circuits. So this is an example of our assembly code. Li is shorthand for saying 8. 20 is shorthand for writing out, 20 in binary. And R0 is shorthand for writing out the 5 zeros to mean register 0. Li again, shorthand for 8, the opcode for a load immediate or load in integer. And 1, shorthand for the number 1, the immediate number 1, which is 9 zeros followed by 1. And then register 1 is short for 0001 or register 1. So on and so forth. So now our programs get a little bit easier to write. We no longer have to memorize the opcodes. We instead just have to memorize the names for the opcodes. Li for load immediate, add for add, sub for subtract, mult for multiply. All right? So we could actually finish off this program by writing it in assembly, by saying, okay, mult R1 or R0 and R1, and store the result in R2. All right? So that would be 420, I think. I don't know. I'm actually terrible at arithmetic. But we'll assume that that's 420. So now, after mult, we can then load 2 somewhere. So we can say li 2 into register 0. And so we load the number 2 into register 0. And now all we have to do is divide register 2 by register 0. So div, we're running out of space here, div register 2 by register 0, store the result in register 2. Why not? So we end up with 210. All right? And I may have messed up the math somewhere, but there we go. These 1, 2, 3, 4, 5 instructions, or 6 instructions, sorry, make up our program for summing the numbers from 1 to 20. But now the question becomes, how do we move to our higher level programming languages? Well, our higher level programming languages get turned into this assembly code that we've just talked about. So in Python, when I say x equals 5, well, that can be translated in a simple way to load immediate 5 into register 0. Although not quite, all right? There is a little bit of a difference here in that our registers are where our computer stores numbers when it's about to immediately calculate with them. But something like x is going to stick around in our program for a long time. So this is where the memory unit comes in. So remember that I said our memory unit stores both our program, our opcode, and the set of it, and our instruction set, or our instructions, and it also stores our data. So this is where our control unit and our memory unit start to work together. So we now can have store word, all right? Or we can even, let's simplify it to store register. So store register, or no, let's make it store word. So store word says, take a register, say R0, and a location of where to store it. And now, what do I mean by location? Well, our memory unit is going to be just a very, very large collection of places where we can store ones and zeros. And we would have a thing in our memory unit called a word, which would be some number of ones and zeros that makes up a word. So a bit is 1 or 0, and you may have also heard of a byte, which is 8 ones or zeros. And then you may have also heard of a kilobyte, which is 1,024 bytes, all right? Or bits, rather. So, oh no, a kilobyte is 1,024 bytes. All right. Now, a word is the basic number of bits that make up a value in our program. So our entire instructions would be one whole word. So our instructions were 20 bits long, which is again weird for a computer. It would typically be a power of 2. Quite often 32 or 64 bit are the size of words in our modern day computers, more often 64 these days. But we're working with 20. And so we need a location in our giant memory unit of words. So our memory unit is just broken up into a series of words. But keep in mind that also our program is stored here. So we will have some number that stores which word is where our memory starts. All right? And so let's say that our memory starts at 5. And so what we have is a special register called the SP, or stack pointer, that points at the memory location of where we last used our store. So the way that we write our instructions for reading and writing words is we write a number. In this case, I'm writing 0 because I want to store it directly at the location of the stack pointer. But then we're also required to update that stack pointer. So I'm going to give us a simple instruction, add 1, that adds 1 to a register. And we're going to say add 1 SP. So if our stack pointer register previously stored the number 5, which is the 5th word in our program, and we stored the number 5 there, 0, 0, 0, or 0, 0, 1, 0, 1, we stored the number 5 there, we don't want the next save of a number to overwrite that 5 that we just stored. So we add 1 to the stack pointer to make it 6, and so the next time someone saves directly to the stack pointer, they're going to save in this free memory here, okay? And that's how our higher level languages, at least for a simple expression like that, can get translated down to machine code. Now, again, we have more complex instructions, like in our higher level languages. Like we have if, we have loops like while, we have loops like for, etc., etc. So how are those achieved? Well, remember that I told you that the control unit would have instructions such as go back some number of statements or jump forward some number of instructions. Well, that is how our loops are done. Except it also is going to have special guards in those conditions, which are if this value is 0, or if this value is less than 0, or if this value is greater than 0, then do this jump, which switches back how many, or forward or backwards, how many instructions we'd like to go. And so that's what an if would look like. An if would look like, you know, if this value is not 0, jump forward 5 instructions. If 5 instructions is what makes up the body of that if. So for those of you who haven't programmed before, in Python, we could write something like if x is equal to 5, and then we'd put a colon, and then we'd write other instructions. So I could say y equals 20, z equals y plus 5. All right? And that is where our if ends. Okay? So what this would look like is if we have, you know, jump if equal to 0, we can say load the number for x into one of our registers. Subtract 5 from the number in that register that we just loaded. Now that we have subtracted 5 from it, we can say jump if not equal to 0. I'm going to call that JNZ. So JNZ means jump if not 0, and that's going to be whatever register we stored the result of x minus 5 in. So let's say register 3. So what would those full instructions look like? Well, those full instructions would look like load word, which is the opposite of store word. So remember that we stored x at location 5, and so we'd say load word into register 3, and we'll say -1 from the stack pointer, if this is a continuation of what we had before, because we have to go up 1 word from the stack pointer. Then we'll say add or load immediate 5 into register 2, and then we'll say sub register 3, subtract from it register 2, and store the result in register 3. And now we can say jump if not 0, register 3, and then we say how far we want to jump. So if y equals 20 is 1 instruction, well, it's not. It's, remember that y equals 20 is load and then store, so that's 2 instructions. And this is going to be load a 5, store the 5, and add those 2 registers together and then store. So z equals y plus 5 is actually 4 instructions. So to skip over this if it's not 0, we have to jump 6 instructions. So we write a 6 there to say if register 3 is not 0, jump 6 instructions in the future, which will continue us in our program down there. So how do we get from Python or C or C++ to our assembly code? Well, it depends on the language. Python is what's called an interpreted language. So there's actually another program running at the same time that reads the Python program and then executes things. That program, however, called an interpreter, had to have already itself been turned into machine code that the computer can understand. So at some point, a program was written in a language that's called a compiled language, like C or C++, sort of Java to an extent, but it's a little bit different because it runs in a virtual machine. So a language like C is compiled. So you write your instructions in C, and then you run another program, which had to have been compiled itself, or maybe it was written directly in machine code. It wasn't, but that's okay. You run this other program called a compiler. A compiler takes your high-level code and turns it into these required assembly instructions. So when it sees if x is equal to 5, it knows to load the value for x, load a 5, subtract 5 from the register where x is loaded, And then it says, well, jump if that register is not 0. So a compiler is a program that translates these high-level instructions into assembly code. Now, it's worth noting that it's not going to be strictly using the stack pointer. It's actually going to have other ways of remembering where it's stored named variables, but we don't have time to talk about that. So the compiler takes this high-level code and turns it into assembly code. And then another program, a quite simple one called an assembler, takes the assembly code and translates it to the ones and zeros that we started with. So we started from writing machine code, then we saw how we can make a shortcut for machine code with assembly code, and then we can make an even greater shortcut with higher level programming languages and turn those into the instructions that computers understand through first compiling the high level code, then assembling the assembly instructions that it produces, which then turns it into machine code that the computer understands. Now, this is actually quite a complex topic. There's a lot more to it, and we've jumped over all sorts of more intricate details. But hopefully that gives you at least a high-level idea of how these computers are set up, circuitry set up, to understand specific sets of high and low voltages to do specific tasks. Now, we've only just brushed the surface, but you can learn more about this if you come and study computer science. And I hope to see you, if you have more questions about this, at the question and answer day in the coming week. All right, take care.